Today we are going to be finishing up the other types of polynomial functions and power functions that don't classify into quadratics or linear functions or exponential ones, hence why they're titled other functions. So you all are going to learn how to write and solve other functions today. Pretty straightforward, pretty simple. So let's get started. All right, so let's solve our power and polynomial different types of functions. Now, a power equation is an equation that can be written in the form of x to the n equals k, where n does not equal 0. So that could be x to the third equals 2, x to the fourth plus a constant equals another number, so on and so forth. But basically, a power equation is when your exponent, basically when you're being raised to an exponent, whether n is a positive integer or a negative integer. Okay? And to solve it, you just go through your algebraic processes like you would if this was a quadratic equation. So for example, 1, we have x to the fourth plus 5 equals 15. You need to isolate x just like before. So how would I do that? Subtract 5 from both sides. So this gives you x to the fourth equals 10. And then how would you get x by itself?
Log.
Not log. Log is if you had your variable in the exponent, but I have a number here. You would take the fourth root. Because if this was x squared equals 10, what would you do to solve for x? You do the square root. But because this is now a power of 4, you would do the fourth root of both sides. Okay? So then what you would do in your calculator, let me show you how to get to those higher power roots. In your calculator, you would go, if you have a more updated version, like you have the apps option on your calculator, all you have to do is press math, go down to option 5, and it basically pops up a blank radical. So if I'm trying to do the fourth root of 10, I would type in 4 here, and then 10 here, and then I'll have my answer. If you have an older version, though, one that doesn't allow this feature, you actually have to type in the index first, what a root it is. So if it's the fourth root, you have to type in 4 first, then go to math, option 5, and then type in the number. Okay? The older version calculators, it'll probably look like 4x root parenthesis, but it's the same thing. You just have to do the index, the root first, and then go to math, option 5. Okay? So 3 significant figures, what is it? 1.78. Good stuff. Can you guys do example 2?
Yes.
Okay. So for example 2, if I'm trying to solve for x, I need to isolate x. That's x minus 2. That quantity to the third power equals 11. What am I going to do first?
Distribute the exponent.
If I distribute the exponent, that's the same thing as saying x minus 2 times x minus 2 times x minus 2.
Wait, do you have to FOIL?
That's a lot of work.
That is a lot of work, especially when I'm trying to solve.
Why don't you just get rid of the 3?
How do I get rid of the 3?
The same thing we just did.
So you take the cube root. Isolate your variable. Basically, anytime you're isolating, you're undoing what's happening in the problem. So if it's being raised to the third power, I got to get rid of the third power by doing the cube root. So that gives me x minus 2 equals the cube root of 11. And then to get x by itself, what would I do? Add 2. So then this would be 2 plus the cube root of 11. That would be the exact answer. And then, of course, I can get the decimal approximation by going into my calculator. 2 plus, how do I get to the cube root again?
No.
I go to math. Now, in math, they actually do have a cube root option. It's option 4. Okay, but you can still use option 5 as well to get a cube root. 3 significant figures? 4.22. Now, one thing that I forgot to mention on example 1 that I need to mention, okay, and I'll use this example I gave as a reference. If it was x squared equals 10, you would take the square root of both sides to solve for x. Whenever you take the square root of both sides in an equation, you cannot forget what?
Plus or minus.
You can't forget your plus or minus. So this would actually equal plus or minus the square root of 10. That doesn't only apply to the square roots or the powers of 2, it's to any even root. Any even root that you end up taking, like the fourth root, it is plus or minus that number. So go back in and add in plus or minus to your 1.78. Now it's fully correct. Okay? So anytime you take an even root, you want to make sure that you don't forget your plus or minus. Questions? Example 3. This is x to the negative fifth power equals 32. We've dealt with negative exponents before when we did laws of exponents. Yes?
So why don't we do the plus or minus on example 2?
Oh, because cube roots, there is only one solution on those. Cube roots only have one possible solution. Any odd root, really. Fifth root, seventh root, ninth root. It's only for your even roots that you have to remember your plus or minus. How to take care of that negative?
Root 1
negative
over x to the 5th.
1 over x to the 5th. You won't be able to do any negative roots.
Oh yeah.
It only works for your positive roots. But we can turn it into a positive by using our law of exponents and do 1 over x to the 5th. And then just a little bit more algebraic processes to solve. Okay? How do I solve for x? What do I need to do?
Multiply
By what?
x to the 5th.
Okay? Anytime your variable's in the denominator, yes, multiply both sides by the denominator to get it out of the denominator. And then you would divide by 32. I'm trying to isolate my x. Remember, x is not in my x is not an exponent, so no log necessary. What do I do at this point?
It's going to be the 5th root of 1 to the 36. Or 1 over 32.
Take the 5th root. Okay? Now, if this was an SAT question on your non-calculator section, you would need to know what number multiplied by itself 5 times gives you 32. What number is that? What number times itself? Say again?
2.
2. So when you're taking the 5th root of 1 over 32, you're taking the 5th root of 1, which is 1, and then you're taking the 5th root of 32, which is 2. Now, granted, for IB, yes, you're able to use your calculator all the time, but y'all still got to take these exams. That could very well be on your non-calculator section. Now, in a polynomial equation of n degree, you can have up to n real solutions, okay? So if you have a polynomial that's to a degree of 2, that means you're going to have up to 2 solutions, 2 real solutions when you're solving. If it is if n is 3, if your degree is 3, that means you can have up to 3 solutions, all right? So when you're trying to solve a polynomial equation, in example 4, that is a quadratic. We did spend some time solving quadratics. However, we're not going to solve it using quadratic formula, factoring, anything like that. This particular section is more so making sure you guys are still capable of using your calculator to solve these different types of equations. So, to solve an equation, you go into your graphing feature, y1, y2, see where they intersect. So in your calculator, I'm going to type in the left side into y1, just like before. We've done this, I don't know how many times already this year. And then you type in the right side into y2. Now for the do now, I did have to adjust my window, so I probably want to take it back to a normal window. How do I do that?
Zoom 6.
Zoom 6. And since it is to a degree of 2, I should have at most up to 2 solutions. 2 points where these 2 equations intersect each other. Do I have 2?
Yes.
Yes, I do. Okay, now remember, it's up to. It's at most. So you could have less than that. Depending on the function, they might only intersect a handful of times. Okay, it might not be up to the degree. So of course, second trace, option 5. Since I have two intersections, I want to move my cursor closer to the intersection point I want to find. So if I'm trying to find the one on the right, I move closer to the one on the right and click enter 3 times. What's my solution? 1.12. And you are only wanting the x value. When you're solving an equation, it's only the value of x. So even though you get a point at your intersection, you only want the x value. To find the other one, I have to do the exact same process. Second trace, option 5. This time I move closer to the left intersection point. If I don't, it's going to give me the same intersection point that I just found. Enter 3 times.
-3.12.
Very good. X equals -3.12. If you also want to provide a sketch of the graph, that suffices as a method, as showing your work, because essentially that is what you're looking for. You're looking for those two intersection points. So that's something else you could do as well.
If you didn't draw that, would you lose another point?
No, you wouldn't lose one. But let's say you had the wrong solutions. Say maybe you didn't click 3 times, you only clicked twice or something. Then at least you can get a method because you knew you were looking for those intersection points. You just found the wrong thing. Questions on this? Can you do example 5?
Yes.
Okay. How many solutions did you have for this?
1.
You had just one. So remember, degree of n, you can have up to that many solutions, up to 3 solutions. In this case, we only have the one, that one intersection point. And what is that solution? 4.11?
You said we can have like 3 solutions?
You could have up to 3 solutions. And that's because this has a degree of 3. The degree of any polynomial equation is the largest degree or the largest exponent in the equation.
My graph has a horizontal line.
Check your window. Is your window? Direct variation. Okay, direct variation still is associated with other types of functions, okay? 2 variables are directly proportional if multiplying one of them by a number results in the other being multiplied by the same number. So basically you're looking at 2 variables, and you'll know that they're directly proportional if you multiply one of them by a number and you get the results by multiplying the other variable by that same number. One of the notations that's associated with direct proportionality is y alpha x. That symbol in between y and x is an alpha symbol. It is the Greek letter. Okay, it kind of looks like a fish. Okay, it's not an actual letter A, but it's a symbol. And the formula for direct variation is y equals k times x. So that is an equal sign, but it's y equals k times x, where k is known as your proportionality constant. In other words, the number that you are multiplying your variables by. So, how is this used when you're trying to solve a problem? In example 6, it says, suppose p alpha t, in other words, that is the notation for direct variation. Instead of y, we have what? P. Instead of x, we have t. So using this equation, it would be p equals k times t. All I'm doing is substituting in the appropriate letters, so then that way when I create my equation, I know exactly what to plug in. Now it says that P is equal to 17 when S is equal to 5. We need to find T when P is equal to 60. Now, the one thing that we do not know that's connecting these two variables together is the proportionality constant. So you need to use the information that you're given, which is this right here, to find K, to find that constant. If you see the relationship between the two, then from there you're able to solve the equation. So we'll plug in 17 for P. We'll plug in 5 for T. So this, can I write it as 5K? Is that going to throw anybody off? Okay. How do I solve for K?
Divide 5 by both sides.
All right. So that gives me 17 over 5 is equal to K. This is my proportionality constant, which means that my equation to represent this situation is P equals 17 over 5T. And now that I know my constant, I'm able to find T when P is equal to 60. I just plug in 60 for P, and I solve for T. How do I solve for T?
Divide.
So if I divide both sides by 17 over 5, that's the same thing as doing what?
Multiply by 5 over 17.
So go ahead. What's 5 divided by 17 times 60?
300 over 17.
Doesn't go anywhere? No. Doesn't go any. It does not go in evenly.
No.
What I did was that I divide 17 by 5 and I got 3.4. So I just divide 60 by 3.4.
That's fine. Same thing. And then you'll get the decimal version of that fraction. So, in this particular example, where your dependent variable was 5, and your independent variable was 5, and your dependent variable was 17, the number that you can multiply to your t's, that you can multiply to your p's, was 17 over 5, and we used that to figure out the value of t. Questions?
I did that a different way and I got the same answer.
Okay. If it works every time, then we can use that. Suppose d is directly proportional to z squared, and that d is equal to 14 when z is equal to 5. We're going to find 1, d when z is 15, and 2, z when d is 140, given that z is greater than 0. So, keyword in this problem is directly proportional, which means you need that formula of technically y equals k times x, again, where k is that constant. But in this particular problem, we do not have y and x. We have what two variables? D and z. More specifically, we have z
Equals dx.
We have z squared.
Okay.
Okay? We're going to plug d in for which variable?
Okay. D as a.
You said Z or D?
D. D as in dog. We're going to plug that in for y. K is still our constant, so that needs to stay how it is. And then x is what?
Z squared.
Z squared. So this is the equation that you would set up and that you're going to use to, one, find your constant, and then actually answer I and double I. In order to answer either of these, you're going to need to kind of know what that constant is. Okay? So, given that D is 14, when Z is 5, we're going to plug 14 in for D, and then plug in 5 for Z. And we're going to solve. 5 squared is?
25.
So how do I solve for K?
11 and 5.
So K is equal to 14 over 25. Now I am leaving these as fractions because if it's a decimal that doesn't end, I definitely don't want to round this to continue to round when I actually answer my questions, because then you're just going to be further off. Okay? Remember, we don't do any premature rounding. We only round at the very end. So our equation,
140 equals 14 over 25 times
okay? So yes, at this point, we are going to plug in. Wait, are you doing I or double I? Okay, so you must have already did I then.
Oh, I thought we just did.
We needed to know what our constant is in order to answer I and double I. So we're going to find D when Z is 15. So then we'll just plug in 15 for Z and solve. And then for double I, we're going to plug in 140 for D and solve for Z. Can you guys do both I and double I?
Yes.
What did you guys get for I?
126.
126, good stuff. And then what about here for double I?
15.8.
15.8? Yes?
Yes.
Okay. You divide both sides by 14 over 25, or you could multiply both sides by 25 over 14. And then how do you get Z by itself?
Square root.
You take the square root. Now, I mentioned it before, when you do the square root of both sides in an equation, you cannot forget your what?
Plus or minus.
You can't forget your plus or minus. Now, I want to specify that because even though it does give you the stipulation that Z has to be greater than 0, if it says Z is less than 0, they will want the minus answer. Okay, so don't forget your plus or minus. It is plus or minus 15 point what? 8 for Z, but your final answer is the positive 15.8. Questions on direct variation? So the main thing to take away from direct variation is that this is the general setup. And if it tells you that one variable is directly proportional to another variable, then that means you just trade out your y and your x for those respective variables. Make sure you find your constant first before you ever start solving the problem. Inverse variation. This time, when two variables are inversely proportional, then that means when one is being multiplied by the constant, the other is being divided by the same constant. The notation for that is y alpha 1 over x. But then this is your general formula for inverse variation. That is k divided by x. Y equals k divided by x is inverse variation. So direct is the product, inverse is the division, and it's still set up the exact same way. Y is inversely proportional to x, so you'll have y equals k over x, and that y is 12 when x is 10. You use that information to find the value of k, your constant. How do I solve for k? Times 10 to both sides. So then k is equal to what? 120. So your equation is y equals 120 over x. This equation is what you use to find I and double I. Can you guys go ahead and do that, please? Okay. So pretty straightforward once you have the equation. So it's important that you create the equation first, find that constant, because for I, all I do is plug in what? 4x. So that's 120 divided by 40, which is easy enough. And then for double I, I'm plugging in 4, and then you're solving for x, okay? Of course, be careful on this. To get x by itself, you want to multiply by x, and then and x is equal to what?
120 over 19.
120 over 19. You can always leave it exact, or if you round three significant figures,
6.32.
remember, you can either leave it exact or round it to three significant figures. Questions on either of the variations? Now, these particular inverse, oh, wait, there's one more example. Okay, I want you guys to do this one on your own. So how do we set this up before we start finding constants and things like that?
P equals k over n squared.
Very good. It was inversely proportional to n squared. So P represented y, and n squared represented x. Very good. So then you had to find your constant. What did you find your constant to be?
1440.
1440?
Yeah.
Very good. You had to plug in 40 for p, and then 6 for n. 6 squared is 36. So then you'll multiply 36 to both sides. So then your equation was p equals 1440 over n squared. From there, you had to plug in to find I. What'd you guys get for the value of p?
120.
Okay, for I, because P equals 1440 over 12 squared, so P would be 10.
It's a 10, 120.
Yeah, it's 10, probably 10. But it's 12 there.
Okay. 12 squared is 144. So then that would be 10. Then for double I. So here, you're finding n when p is 90. So just like before, you're going to multiply both sides by n squared. Divide both sides by 90, so n squared equals
16.
16 even?
Yeah.
Very nice. Then I have to do what to find n?
Square of both.
Make sure we take the
Plus
square
or
root,
minus.
plus or minus 4, but we look specifically at the problem, n has to be
Plus.
greater than 0. So it's positive. Okay? So make sure that you're using those general formulas of y equals k over x for inverse variation and y equals kx for direct variation. Here we go, the last example, okay? Look at the application of how variation is used. The company manufactures ball bearings of different sizes. The table that I do not have on here, but I'm going to add in just a second, shows the radius and mass of each type of ball bearing. We're going to create a scatter diagram of the data. We're going to obtain a power model that best fits the data, and then we're going to estimate the mass of the ball bearing with a radius of 22 millimeters. So we have to create a scatter diagram of the data. A scatter diagram is nothing but basically you plotting your points on a graph. Okay. We aren't given the scale in which to do our data, so we need to create one ourselves. Okay. Our horizontal axis is going to represent what? Radius or mass?
Radius?
It's going to represent radius, and our vertical axis is going to represent our mass. Easiest way, whatever they give you first, that's always your independent variable. It's never the other way around. This is always your x and this is always your y, every time. All right? Make sure that whenever you are graphing something yourself, you label your axes. So this is going to be radius, and this one over here is going to be mass. You always label your axes. And then, of course, since we have to create our own scale, let's try to figure out the best scale for our centimeter paper. So, again, what you have on your notes is centimeter paper, where every 5 lines or every thick line represents what? 1 centimeter, okay? So, if you notice for our radius, we have 5, 8, 10, 14, and 18, and we basically have 4 centimeters. What would be a good scale for our centimeters?
5.
By 5, starting at
The origin.
0, okay? So then this will be 0 here. And every centimeter is going to be 5, so 5, 10, 15, and 20. Does that cover all my radii?
Okay,
Yes.
you mean millimeters?
No, every centimeter in the centimeter graph paper will represent 5 millimeters, yes.
Okay.
Yeah. And looking at my vertical axis, my mass axes, we have 4, 16, 32, 89, and 190. And again, we have 4 centimeters for our graph paper. What would be a good scale for that?
Every centimeter equals 50 grams.
50, because mass is in grams. So let's see, 50, 100, 150, and my top one is cut off, but at the top 200. Very good. Now the last homework assignment that you had, I just want to make sure, wherever you draw your x and y axes, that's where you put your numbers. Okay? Do not put them in the wide open space unless that's where your X and Y axes are. But I made a comment to all those who did that on the last homework assignment that you turned in. Not exponential functions, the one before that. So now we got to plot our data. So at 5, we're at 4.08. Well, if my Y's are, every centimeter is 50, that means that each one of these lines is what? 10. So 4 is going to be very close to 0. 8, 16. Let's see. Every line on my x-axis is going by what? 1. So I actually can go over to 8. Here's 8. And then I need to go to 16. So that would be in between the second and third line. Okay. At 10, I'm at 32. And then again, we're just graphing here. Okay. Scatter diagram is nothing but plotting your points. 14 would be one line before 15. And 89.65 is very close to 90. So I'm right below that 90 line. 18 is 2 before 20. And 190.54 is right above the second to last line. And there's your scatter diagram. Sometimes scatter diagrams are used with X's or little boxes, something other than points. But when we get into statistics, which is after functions, we'll get more into that in depth. Now it says to obtain a power model that best fits this data. To do this, we need to go into our calculator. And because we are dealing with the data, we need to type in our data. This is a great exposure to what we're going to be spending a majority of the next unit doing. So let's do this. Since we are dealing with the data, you'll need to press the Stat button, which is located 2 buttons to the right of your Alpha button. And you should have this screen. Then you want to actually click Enter on Edit. Okay? So you're at Edit, you click 1 on Edit. Now, I don't know if anybody has any data in L1 or L2. Raise your hand if you have any data. Okay. If you have some data, don't do what I'm doing if you don't have any data. Okay? So if you have data there, you go up to L1. Make sure L1 is highlighted. You click Clear. And you click Enter. Clear. Not delete.
Why didn't we press delete?
You want to see what happens when you press delete?
Yeah.
It deletes the entire column. You don't want that. You want your L1. Okay? So if you accidentally press delete and you delete one of your columns, all you have to do is you go back to Stat. Remember, that's what we press to get to the list. You go to Option 5. And you click Enter. So Stat, Option 5, and Enter. So then that way when you go back to Stat and you go back to Edit, it's back. All right? Now, we need to type in our data. We're going to put radius into L1, our mass into L2. X into L1, Y into L2. So everybody, let's type in your data. You click the number and you click Enter. That's how you register in the data. So you have to click Enter after every time. You just press the over arrow to move to L2, and then you type in your mass into L2. Pressing Enter after each entry. So now that we have our data in, now we're able to find that power model that the question asked us to do. So what we need to do is we need to go to second mode. Second mode quits out of our list, quits out of our data, okay? So we want to go back to our home screen. And then we're going to go back to Stat. You want to go over to Calc, C-A-L-C. And since it asks us to find a power model, we want to scroll down to where we see power reg. Okay, you'll see all these other options. Like option 5 is a quadratic, 6 is a cubic, 7 is a quartic, 8 is a linear, 9 is a logarithm, 0 is an exponential. Like, the calculator can create each one of these types of equations. But since we're looking for a power model, we want to go all the way down to PWR rev. It's A for me. I don't know if it's for everybody else. Okay? So when you click enter, this is another thing that the older calculators and the newer calculators can differentiate. So if your calculator looks like my screen, follow along. Okay? Follow along. You want to make sure that your L1 is your X list. To get L1, if it's not already there, you press the second button and then you press the 1. That's how you get L1. Your Y list should be your L2. That was your mass. So second 2 is how you get L2 if it's not there. Everything else should be emptied. There shouldn't be nothing in frequency list, nothing in store. All that should be empty.
Miss Addison?
If something is there, then you go down to it and you click clear.
How do you get to A?
Just scroll down. Is it not there?
Oh,
Do you mean like without pressing enter?
yeah, I found it.
It's out.
And then you go to calculate. And now we have our power equation. Now, before I talk about this, I need to catch everybody else whose calculator doesn't look like this. Okay? So, if your calculator has R squared, don't worry about it. We'll talk about that more when we get to statistics. Raise your hand if your calculator just shows this when you went to the power function. Okay? So what you're going to have to do is you basically have to tell the calculator that you wanted to create a power function with L1 and L2. So you'll just type in L1, so second 1. Then you'll press the comma button, which is located right above the 7. And then second L2. Okay? And then when you click enter, you'll get the same thing that everybody else got. So now we have our power equation. It's basically showing us exactly how we should write it. That y equals a times x to the power of b. That's what we write. And then here's your values for a and b, of course, rounding to 3 significant figures. So our power function, going back here, is going to be y equals, what was the value of a? 261. So then round 3 significant figures, it would be 0.0326 x to the b power. What was b? So then the 3 significant figures would be 3.00. And then that would be your power function. Yes?
How do you got 0.0326?
From here.
Okay.
So the first line tells you how the equation is written, and then you write it as such. And now you have your power equation. And you can use that equation to find C, which says to estimate the mass of the ball bearing with a radius of 22 millimeters. And actually, let me fix this equation before we do that. What did Y represent? Mass. So I'm going to replace Y with M. And then what did X represent?
Radius.
So I'm going to replace X with R. So then that way, when I do answer part C, which asks me to find the mass with the bearing of 22 millimeters, I'm plugging in 22 for R to find my M. What'd you get?
Miss Addison,
Mm-hmm.
that's supposed to be C, not D.
What's my mass?
347.
3.7?
347.
3.47 grams.
Just 347.
Oh.
Yeah.
Just 347. Okay, my mistake. I'm sorry. Like this?
Yes.
All right? Which makes sense because 22 is somewhere over here, correct? And if you look, this graph is doing what?
Growing.
It's growing. It's increasing like an exponential function would. So it would have to be something that was bigger than 190 because that's what it was at 18. So that makes sense. Okay? But that's how you can use power functions, direct and inverse variation to create other equations that you can solve.
And you usually go rounding numbers for your answer, right?
Yes, you will want to in this particular case.
Okay.